Good afternoon, participants. I'm happy to welcome you all for the afternoon session. For today's afternoon session, we have a great expert from 3D printing area. We have Dr. Ravi Kumar, Associate Professor from NIT Warangal, Mechanical Engineering Department. Sir obtained his BTech degree in Mechanical Engineering from JEE to Kakinada and ME in Computer Integrated Manufacturing from TAG College of Technology, Coimbatore. And he completed his PhD in Osmania University. And he also did a postdoctoral research in 3D printing at the Milwaukee School of Engineering, US, in the 3D printing area. And he has completed, that is guided 4 PhD scholars, and he is now guiding 4 more PhD scholars. And he published more than 70 journal papers in national and international repute. And he also have 1 international patent and 2 Indian patents to his credit in the area of 3D printing particularly. And he is very much instrumental in setting up RPT laboratory at NIT Warangal. He is also very much instrumental in starting MTech program in additive manufacturing with the collaboration of CMTI Bangalore, which is first time of its kind in India. And he also experienced in establishing a world-class metal 3D printing facility at NIT Warangal under TechUp grant. He has conducted more than 15 training programs across India and trained around 900 participants in the area of 3D printing alone. He received Young Engineer of the Year 2009 award from Government of Andhra Pradesh and Institution of Engineers India. And he had executed several research projects sponsored by government and private sectors, and particularly R&D project worth of 1.25 crores in the area of 3D printing. And he is a member of IST, Institution of Engineers, and the Rapid Prototyping Society of India. He is very much experienced in the area of 3D printing, and he visited countries like Australia, Sweden, Singapore, Finland, France, and the USA for academic pursuit of activities like that. So that much expert person we are having with us for today. At the outset, my sincere thanks to the professor for readily accepting our invitation to deliver a session during this FTP. On behalf of Murugappa Polytechnic College and my own behalf and Department of Mechanical Engineering, I welcome Professor Dr. Ravi Kumar sir for the session. Sir, now the stage is yours, sir. You can start, sir.
Yeah, very good afternoon. Thank you for your introduction, Professor Shekhar, and the organizers given me this opportunity, and in particular to Murugappa group of institutions, and of course the AICT Atal for the sponsoring this program. So first of all, let me say share my screen. I would like to say, is my screen is visible, sir? Maybe confirm.
Yes, sir. Yes, sir. Started, sir. Visible.
Okay. Thank you. Thank you. A very good afternoon. So I hope this is the second day of the program. By this time, probably you are, say, exposed to the at least some fundamental aspects, and some of the participants may be already exposed to this technology. So my talk during this session will be onto the design for 3D printing. So the design, why you are separately talking about the design for 3D printing? Actually, you may come across design for manufacturing, so DFM concepts, or design for assembly. But how it differs from a conventional design for manufacturing versus design for additive manufacturing or 3D printing, I hope you might have understood that these two words nowadays going in a synonymic way. So means you cannot find much difference between these two words like 3D printing and the additive manufacturing, though you have some narrow differences, but still this word is going, say, 3D printing is a common name that we know that in spite of say narrowing it down to a manufacturing sector, but definitely additive manufacturing is going to be the good word to be pronounced rather than 3D printing. But anyway, so then how your design for 3D printing? What is this? How it differs from a conventional design for manufacturing? Probably you may come across design for manufacturing where your design should be in tune with the manufacturing. Means at the end of the day, your manufacturer should not say that whatever you have designed, it's absolutely not manufacturable through a conventional way. And it should be, your manufacturer should say be comfortable with the design what your designer has been say shared to manufacturer without a difficulty in manufacturability of it. So it should be done and in a more cost effective way also. And coming to the design for 3D printing. So the 3D printing, probably this is a sort of technology where you can make your products from digital data, say, and 3D printing is well versed with the complexity. Whenever you have a complex products, then you are 3D printing with no additional cost, or with which we can say in a more generic way. So it's going to be the complexities are free of cost. Maybe you can put it in that way. But how do you exploit this the free of the complexity in 3D printing? So and not only that, you have some unique advantages of 3D printing. Probably the other speakers might have talked about the part consolidation aspects, or you have lightweighting structures, probably, and say you have nowadays you have a multi structure or multi-material structures, which is easily done through 3D printing, which otherwise it is very tough for the conventional manufacturing systems. But anyway, you have this much the flexibility for a designer, but is that can be achieved, say, in a more effective way? What I'm trying to say here is whether your design is, say, how is your design is to 3D print or through additively manufacture. That is the concept revolving around, say, design for 3D printing. We'll see various aspects of this design for 3D printing. Let us quickly introduce this technology of 3D printing. Of course, if you see the process plan of this 3D printing, it is not like a conventional process plan which you come across by using a conventional manufacturing systems, but you have a different process plan which we need to say follow here. Maybe you start with, say, accepting the STL file and say generating some supports, and then slicing it, and then generating the tool paths, and finally you will be fabricating physically by means of that slice data or the cross-sectional data that has been automatically generated through any of your software which it is interfaced with your 3D printing machine. So we'll focus on the 3D printing process plan aspects, and one among could be the part orientation or the fabrication orientation. Say, it doesn't matter, say, which orientation you have designed, but how do you get fabricated your product, in which orientation, which build orientation, which you're going to. So that's going to matter a lot. So that also we'll see how it is, say your part orientation is playing a vital role in any 3D printing technology. And of course, another one is a support structure generation. Say, how do you minimize these support structures, or say, how do you tackle these support structures? Say, though it is not as a part of your, say, design, but for the ease of your fabrication, which you will be giving the supports wherever it is necessary, maybe some sort of overhang or some sort of undercut, or you have a certain projections, or which we need to give some support during fabrication. So then how do you say optimize these support structures? So this all comes under design for 3D printing or additive manufacturing. So, and of course, which once you set up all these say parameters, then you may be even slicing this model. So then how do you get generated your slices, and of course finally your tool paths. Though you don't have any tool here, but the name, it has been borrowed from the CNC technology. Why? Because it has a DNA of CNC technology. Then tool path is either it could be a laser driven system, maybe a laser path, or even it could be the path of the nozzle that you will be extruding from the material from the nozzle. Then which we need to say generate the tool paths. And how do you optimize these tool path generations? And of course, sometimes which we need to repair the mesh. Mesh means basically a STL file. It's a triangular mesh, and which sometimes we need to do a repair. So why we need to do a repair, that we'll discuss then, which sometimes we need to do these repairs, and then your slicer tools will slice the design, and then you generate the tool paths, and further it has been sent to the 3D printing machine. And your design for 3D printing will comes a beautiful concept of topology optimization, like which you will be optimizing the topology. So means you may be reducing the weight of the structure, or you may be improving the functionality of the structure. So which you have a role that should be played, how your topology optimized structures are getting fabricated. So that is none other than through 3D printing or additive manufacturing processes, and you will be say mimicking the biology in design. So that's what where you have some lattice structures. Not typically you come across in medical applications or aerospace applications, predominantly by bionic designs, and how 3D printing is related to your bionic design aspects. And how do you get select your 3D printing technology and design rules of 3D printing? That's what I have planned. Maybe the next another 1 hour or 1 hour 40 minutes or so. This is the content I'm going to discuss with you. And if you see the typical process chain, like where we need to start with your say design through either through a modeling software, or even it could be done through a reverse engineering data, which you can have a point cloud data and further it has been reconstructed, or even you come across the medical field where you start with CT or a MRI scan data. Even that is also can be digitized, or even it need not be every time the 3D model interfacing, but even it could be generated your data in a digital form. Say you may come across in a different fields. Then the idea here is to digitize your product data. So that digitized product data is getting converted. Just now we are discussed as an STL file, or it could be an AMF file, or even it could be a 3MF file. So your basic idea is to convert your digital data into the 3D printer understandable format, typically STL file, that is a de facto standard, which is of triangular representation, and it is getting transmitted that data to a sort of computer or a sort of interfacing software that is connected with the machine. So you just say import that data and you check for any errors or check for any say whether the data, like you have a STL file, all the triangular facets or so distributed properly or not, like some triangle is missing or it is making some puncture, means without making an watertight model. So which we need to check for those sort of errors. So you may get doubt why you want to check. Unfortunately, neither your CAD software nor your interfacing software for 3D printing machine doesn't have that diagnostic system where whether your model is free from all these errors or not. So then it is mandatory to check for those sort of errors. And once it is free from the errors or whatever maybe the faults or the faulty files, which we need to check them and repair it, and you may be preparing the build setup or to the codes that has been sent to the machine to run something like your G codes and M codes in case of a CNC, which you are going to generate a cross-sectional data. So once you supply all the process parameters like layer thickness, so like if it is a laser driven system, so you have a laser power, or if it is an extrusion based system, so then the melting point temperature of the material, just below that you may be heating it. So just you specify all these parameters, and then you slice it and generate the tool paths or generate the cross-sectional data and send it to the machine, where your physical realization of this digitally sliced cross sections has been realized on a equipment, on any typical 3D printing or rapid prototyping was the earlier name, as we know that. So once you fabricate that, and last step could be the post-processing. So the post-processing could be done through various methods. Again, that depends on what sort of technology you're using it, whether you're using say a photo polymerization process like a VAT based system, then it should undergo a UV curing process. Then only you will get an 100% solid, rather than you maybe end up with say some sort of say 90% or 95% solid, but still you can find some liquidous kind of structures. But it is a mandatory for VAT-based systems to use some curing oven, or even it could be the other technology. Sometimes it could be a sort of powder. If it is a powder-based system, which we need to evacuate the loose powder, or if it is a sort of say a sheet lamination based, you may have a different post-processing methods, and not only removing cleaning and support removal. Even it could be the part of your post-processing will also covers, say, your 3D printed parts or not to your expectations, means in terms of physical properties or in terms of say mechanical properties, microstructural aspects. If you're not say satisfied or not finding the exactness if you compare with conventional processes, so definitely we need to say adopt some sort of say furnace treatment, for example, or some sort of hipping process, or some sort of say finishing operations which we need to perform. Say what I'm trying to say is, so depending upon your application and the required properties and which you may invest say onto the post-processing methods, apart from support removal and apart from your cleaning of the parts so that has been say unloaded from the machine, and you follow the post-processing operation, and finally your application is ready for your 3D printed structure or the product. So this is the process chain of a typical 3D printing process which you come across. Say just you can elaborate whatever we discussed, like which we need to start with the CAD model, and this is a typical the true model, or say the native model, the native representation of your CAD model. Say for example .prt or .part, whatever it is, it's a native representation of your model, the true representation. But at the moment you save it as an STL file, so it has been tessellated or it has been approximated into triangles, and you can control the mesh resolution. So by reducing your card height, or by reducing your say the sort of approximation or the angle control, which you can even say get more precise representation. That is at the cost of more number of triangles if it is an STL file. So typically it is an STL file, that is industry de facto standard for, in as of now it has been right from the beginning. Yeah, then which we need to start with a CAD file with a true geometry, and it has been discretized or approximated into number of triangles, which you can increase the discretization or the resolution by controlling the parameters in your software itself. This is a typical thing where you start with your CAD to STL file, and then next step is we need to slice it. So while slicing it, so again you may adopt different layer thicknesses. Maybe you may go with say fine resolution, maybe 0.05 mm, or even it could be typically maybe even 0.5 mm, or it may be 0.05 mm. So means you have a huge range here. Again, that depends on the type of process you are using it and the material that you're using it. Probably you can choose. So that is dictating a lot on your accuracy aspects. And once you're done that, so next step is we need to say generate a tool path, or if it is a nozzle driven system, which we need to say first create a sort of say outer contour, and that outer contour is filled through if it is a nozzle driven system, then you will be filling that outer cross section through your material that you're using it here. Maybe it may be a laser system, or it may be a nozzle based system, deposition based or extrusion based system. So typically you generate the slice files, those are empty contours, And something like your G code, normally you say you fill that, and finally you have a part density. And again, you have a lot of flexibility here in terms of filling density, which you want to go with, say, 100% dense or 80% dense or 70% dense. So you have flexibility here, like where you can vary the filling density, or the fill patterns which you can make use of. You have a lot of freedom and flexibility to do that. So it may affect your strength, or it will affect on your accuracy and other quality aspects. So you have that sort of, say, a flexibility. So you start with 3D file and STL conversion, and generate something like a layered data, something like a G code, uh, which you will be doing this. And the other aspect which we are talking about is a part orientation. The part orientation that, say, if you take a simple, say, wine bottle, so where you can fabricate this in vertical orientation or some 45-degree or any other angle orientation which you can fabricate. So, but how it differs, say, your part orientation, so influence a lot. Say, for example, which you can see, you have a first layer, second layer, and the last layer, and which you have a less deviation or less staircase effect or less error um, in this orientation than in this orientation. So again, depends on your layer thickness also playing a vital role. But and not only the accuracy, you need to provide supports here, extra supports. So then one can identify or select an optimal orientation in such a way that, say, without compromising your surface finish, on though you have a conflict, or you have a trade-off between your accuracy and the build time. And the of course, we have other criterions that we should consider, maybe the support material, amount of support material that has been required in one orientation to other orientation. So like that, your part orientation, almost it is depending on all the outcomes of your product. And you talk about the layer thickness, like which you have a huge a range of the layer thickness. If you go with very thicker layer as common sense, so it will finish quickly, but you have a lot of error. It means you have the accuracy may not be that much great. But if you go with the medium layer thickness, where you can have better accuracy and medium build time. But if you go with very thinner layers, very precise resolution, where you can have less error, means more accuracy, but it may consume much of the build time. So, but anyway, somehow we need to compromise, or we need to come out with this sort of a trade-off situation, or a sort of say, this is a typical thing. And support structure, again, your part orientation is playing a vital role for, say, the amount of support. If you fabricate this part in this orientation, you may have some X grams of support material it is required. But if you see other orientation, so it may be, say, Y grams of support material is needed. But so you are designed for 3D printing concept, where you can say come out with a better, so less support structure, or rather than by modifying your design slightly, maybe again you can have some matrices, the sort of the quantifying how much we need to, whether your design needs to be modified with the major or minor modifications. So you have a lot of scope that we need to work on the design for 3D printing concepts where you can optimize your resources. So, for example, here the support structure, or even the support structure is going to play a vital role even for the metal printing technologies also, where it is if it is a polymer based system altogether, you have a different scenario of supports, and if it is a metal printing system, you have a different aspect, like how you're going to come out with this sort of say support structure minimization or optimum utilization. So these are some of the aspects which we can elaborate talking on the part orientation in 3D printing. So we have a several criterions, like so whether your part orientation has been done through a sort of height criteria, means your build direction which your part is giving, say z height is minimum, so means obviously the number of slices are minimum. So if your z height is minimum, you choose a orientation so that is giving a less number of slices, rather than, in other words, the z height should be the criteria, one of the criterions. Or your quality, the total surface quality may be the another criterion, and the area of the base on which your part is resting, means the better foundation which you have, the another criterion of fixing your orientation. Or you're looking the mechanical properties. Why? Because you cannot expect the same mechanical property if you make one sample in horizontal orientation and you make another sample in vertical orientation. The mechanical properties never match. So in that case, like, what could be the optimum orientation for your better mechanical properties? And of course, your external support structure, as we are discussing in the previous slide also. So if you take a typical say design, so then you can come out with say, for example, 5 different criterions, means 5 different orientations. In one of the orientation may be the maximum area of the base, so the better foundation criteria, or even it could be a minimum area of contact with the supports without damaging your model. Why? Because we need to peel out or we need to separate it out, the support from the model. We should not damage your model in that action, right? So, and even minimum height criterion, so minimum z height means minimum less number of layers, the build time will be minimized, and minimum facet roughness. So it is a quality aspects, like where you can choose another orientation, and we are looking for a minimum volume support. So you may be fixing this sort of supports the orientation. You may get doubt that, so how do you ensure that which orientation, or software by default it may suggest some orientation. So that may be normally that will be this minimum z criterion, that is the more cost conscious, right? Say consciousness, like where the z height is minimum, the build time is less, the cost of production will be less. So in that aspect, like where you will be coming out with a sort of optimized part orientation, this everything will comes under. So your designing of your product means, while how do you get selected your optimum orientation? That's a part of your design for 3D printing aspect. And even say you have the orientation will also affecting a lot on the accuracy or the surface finish of the part. Say for example, you have some build orientation is some angle theta, maybe around say 45 degree or something like that. And if you try to fix this orientation and you try to fabricate the layers one by one, so where you have x is the layer thickness and y is the exposed parts step, means where you have, this is the original CAD representation, but with the layered phenomenon. So where you have an error, so that error is this much. If you could fix your orientation, your theta angle maybe around 45 degree or so. And if you change the other sample with say 30 degree orientation, so where by fixing the same layer thickness, where you can anticipate say the error, the deviation is much here rather than the previous sample. So one can understand the importance of your build orientation so on affecting your surface finish. And of course, the mechanical properties, as we discussed earlier, also, if you fabricate one sample with this orientation, say, and you try to see the fracture mechanics of this sample versus you have another orientation which it has been say 90 degree orientation, the layers has been laid in this direction rather than on this in this direction, and which you have built, but you have more number of layers here if you compare to here. But the you see the fracture mechanics of this sample versus this sample. So the 0 degree versus the 90 degree orientation, where you have a different fracture mechanics. So then ultimately your what is your required properties, like which it is affecting a lot onto your fabrication orientation. So, and we talk about the cost, the production cost of these 3D printed components. So the total cost would be the sum of a pre-processing cost. The pre-processing cost, which includes, say, you may be hiring design engineer, or you may be hiring application engineer, or you may be hiring some softwares to generate your tool paths, or to sometimes, as we are talking about, say we need to redesign some aspects, say your pre-processing cost, which includes those sort of costs. And of course the build cost means the machine utilization cost for building your prototype or your products. And of course the material cost, that is the model as well as support material cost, if it is the technologies. Predominantly these 3D printing systems require support structure 70 to 80% or more than that, so which we need to work on those costs, plus the post-processing cost, as we already discussed, say, which we need to say cleaning up or removing the support structure, and plus for further in order to improve the mechanical or any other physical or any other properties which we may be incurring a cost towards post-processing cost. So maybe furnace treatment or short pinning for improving surface finish and so on and so forth. But your post-processing efforts or the cost can be reduced if you've done a sufficient homework here with a sort of pre-processing, say, step while design for 3D printing concepts you bring here and optimize whatever we are discussing in the previous discussions. So just you can try to say design here itself those aspects. So considering those aspects here, even you could be able to reduce the post-processing cost also if you have done sufficient homework and better using it. So this is a crucial part. Why? Because more or less the machine is automated, so nothing to do much on the machine side. But whereas this is the main crucial part of your, say, as the cycle you do in a 3D printing process. And of course the cost is also, and then support structure generation, as we discussed, like where nowadays this support structure, I hope the previous speakers might have talked about various processes, but the support structure definitely it will have different say outcomes or it may behave differently. Why? Because sometimes you may work with the polymer-based system. Sometimes you may work with the metal-based systems, which you have totally the conductivity or the rate of fusion of the particles, or so you have these support structures even on seeing, and again, which you may not be able to say generalize support structures. Why? Because each material behaves differently, and you may use some photopolymerization process sometimes you may use powder bed system, and sometimes you may use a binder jetting or a material jetting system or sheet lamination based system. But you must know about the behavior of the support structure from one process to other process. But in a general thumb rule, so your say for example, you take an extrusion based system like say your FFF, that is through an FDM based say DIY kinds of systems like filament based systems. Typically you may see that the support overhang for more or less than 45 degree, and even it can be applicable to other processes also, but some of the processes, but this is a general thumb rule, but you have to modify accordingly the type of technology and the type of material you are using it, so it behaves differently, right? So, and you can come across several softwares to do this job. Maybe Simplify 3D or the Cura is another software where this more or less it is an open source software and maybe supporting to a sort of FDM based or filament fusion based systems, which you can see some of the softwares. And then if you see the support structure, so normally you can divide these support structures into three categories. So the first category could be the separator kind of a support, means you have the platform where you are going to start depositing the layers. So initially you put some layers, maybe some 10 layers or so, that will directly say fuse onto the substrate or a platform. So where you use this kind of a separator kind of a supports, where it will give more reinforcement, or where it give a more say basement of your part. And of course you have a main supports which is of say which your main supports does not directly contact with the model, and you have the third kind of a support which it is directly contact with your model material, that is a Sierra or a needle kind of a support. So you see these supports in a different perspective, and accordingly you say design on and print this supports. What I'm trying to say, you can vary the infill density, or you can vary the path strategy for different regions, basically. So then you can work on these things. Why? Because you may have a different kind of function for a separator kind of a support versus the main support versus the needle or a Sierra kind of a support. So by considering those aspects, so you can design your support in different or in tune with your thing which we need to design and fabricate it. That's way of doing. But software may give a default. I do agree. So software may give some default styles of these supports. But though you can even come out with your more optimized thing, which it may not be true for all the geometries and all the materials. Sometimes we need to customize them. So and support structure does not always has been a curse for you. Say, for example, if you are not providing a supports here, so you have a separator kind of a support here, and but you didn't give any support here. So because you're not given a support, So you may anticipate some sort of a peeling or a curling effect or peeling effect of your layers. So then if you provide some support, you can eliminate this sort of the curling or a peeling kind of effect. So you can with the support structure. So, but not always support structure is harming your thing, but sometimes so it may be very much needed. Maybe again that depends on the type of material and the type of process you are using it. So sometimes which we need to support material will act as a conductor, maybe to in order to say take it that dissipate the heat. So sometimes it is quite obvious which we need to come across. Maybe it may act as a sort of conductor in some other situations or the applications, but we cannot generalize saying that always the support is bad. And then of course we do slicing of this thing and toolpath generation, how you're going to and of course once you have set everything and then which we need to start slicing it, your CAD model should be sliced. And probably if you see the mathematics behind this is simple math involved, that we are working with an STL file. More or less it is a triangular facets. So it is a simple mathematics or a geometry involved here. So of course Z max is the maximum height in Z direction and the minimum height in Z direction by your thickness, the layer thickness. So it will give you the number of slices that your model consists of. And then how do you get your slice point? Means once you use some cutting plane and you try to slice it, and your cutting plane may be touching one of your triangular facet. Why? Because your model is an STL file. Basically, it is a triangular element. So that triangular element, which it is intersecting with your slicing plane, so you can easily calculate your coordinate of that sliced point, the X coordinate as well as the Y coordinate. Of course, at that particular Z layer instant, for that instant, maybe at a particular layer number, so which you could able to get this coordinates of your slice points. And once you'll get that coordinates of the slice points, what I'm trying to say, you have a model STL representation and you have a slicing plane. I'm talking about these intersection points. So I have intersection point 1 here, for example, 2 here and 3 here, and across the periphery. So I have 1, 2, 3, 4, 5, 6, 7, and of course 8, 1 and 8. So then only it will form a closed loop and ensure that it is a one contour, or at this layer position you have this cross section. So and typically you can have two notations, either it is a clockwise or anti-clockwise. So depends on whether a sort of that data belongs to interior or exterior. So initially, which we can come out with this kind of a syntax and semantics of it. So once you get this contours, and of course, which we need to obviously check for some sort of peak features. What do you mean by a peak feature? Is, say, for example, you're slicing your model and your slice thickness is this much, but whereas your feature, which is of lesser thickness than the layer thickness, the resolution, then of course there will be a chance that you will lose this feature. It cannot be recognized. So then, like that, wherever you have that sort of peak features, you identify those peak features. You should not lose them. Then, for that matter, which you may adopt a different slice thickness for that thing, and where without losing your data. So, and again, that depends on what is the layer thickness you are adapting and what is sort of minimum feature that you can get it from that machine, and then which we need to even evaluate for that matter. So which machine you are going to fabricate this, and what could be the resolution of that machine, and the minimum the feature that you're going to get. So we need to say check all that aspects. Though it is a push button kind of approach, we do agree that 3D printing is something all about a push button. Just you take an STL file, your CAD model, slice it, and everything is automatic and absolutely fine. But which you have see the practicality, or which sometimes you may miss these sort of features, right? So then we have to explore these sort of gaps where you can encounter. And once you identify the peak features and you have generated the slice points, and if you take at a particular cross section, a particular layer, so you may have several what you call the features at that particular layer. Why? Because it's a combination of different features. Again, that depends on the geometry of your model, of course, and we need to have a sort of a parent to child relationship, right? So which part may be the parent and which part could be the child, and how many generations it may go, something like that. Say, which we need to say organize these. But you may wonder why I'm saying all this, but your software may be doing it for you. But everything will be done and everything will be organized. It's fine. So ultimately, these organization of your say the contours have been done, and each and every layer of your model. So I have 100 layers, so which you can say anticipate all 100 layers. You organize this data and generate your say ultimately we need to say send this data, something like your G code, M code data, something like it. And now I'm calling this as a CLI. So this is one of the file extensions you may use. So this is basically a contour data. So after say slicing and generating the cross-sectional data, now it is the cross-sectional data in this format, and where it consists of your how many number of layers that a typical design is having, and the first layer. So it consists of everything, right? Say the index number and the layer number and Z coordinate of that current layer. And this starts with the first layer. So I have some 10 number of contours at a particular say cross section. So then the first contour, so I may have the contour number and whether it's a closed or open, and whether it's internal or external, or even it could be a father to a child, or so some sort of say that hierarchy thing, and number of contour points that is having for the first contour, and of course the coordinates of that. So the coordinates of that, and that is one contour, and typically it may have several contours, and the information about each and every contour, second contour, third contour, and the last contour. And that's about the first layer. And go with the second layer, and the same thing will be repeating. So depends on the geometry which you have different contours here with the second layer, and you have the last layer up to this sort of data, right? So this is basically a sort of polyline data which it is fed to the machine to run the show, right? And finally, so you have the external cross section of a particular cross section, this geometry, and then how it is getting filled. So I can fill it in several ways, maybe a combination of horizontal, vertical, or some sort of inclination or zigzag or contour, and you can come out with a different toolpaths. Why I'm talking about this? So means like it will dictate a lot on your outcome of the product, maybe the density for that matter, or the mechanical properties. So which it will be varying from one path strategy to other toolpath strategy. So then it is our job to come out with optimum utilization of these toolpaths. So then of course, what is your the requirement? So you are looking for what sort of application your product, so what sort of design requirements, and based on that, which we need to do all this exercise, right? So and we talk about the mesh repair and slicer tools. Typically, we are talking about, say, the mesh in the sense is a triangular mesh. I'm taking only the STL file, and of course some slicer tools that should be done. And you can find some proprietary softwares to do this job. Why we need an STL editor or STL modification or diagnosizing your STL file, as we discussed previously also. Unfortunately, your CAD system doesn't have this diagnostic kind of mechanism, nor your interfacing software doesn't have this. So that's what you may be adopting some, say, third-party software where even it will allow you to do an STL editing. So first of all, why you want to edit the STL file? As we discussed, maybe some errors or some text should be mentioned on that, or labeling purpose, or visualization purpose, measuring purpose. You may get doubt. You can take the measurements on your CAD file, right? So you are correct, but you cannot take the measurements on STL file. Once you save it as an STL file, so it will become a static model. You cannot do much of these operations on your STL file. But again, you may go to your native file format like .prt or .part or whatever it is. So, but that is not a good idea. If you are running some service bureau, and then that's not a good idea to send back your model to the customer, say, asking that, hey, can you modify this? Or that's not a good idea, right? So just you have these sort of say tools with you. You can do sometimes applying different colors, paintings. Why? Because your STL file is a monolithic file. It won't support any color. Rather, it won't support any material as well. So then your much of the 3D printers can print in different materials, multiple materials, functionally graded materials. So then, unfortunately, your STL file does not represent these maybe material, maybe color, say maybe attributes, any other attribute, material assignment, which it won't support. So then you may approach other tools or other file formats like nowadays. But not all the 3D printers can take like AMF, 3MF, OBJ, or MLT files. But if some of the printers can take that, but you can do directly giving that data. But still, you don't have an option. Your machine can take only STL file. So then we need to do all this exercise. So whenever it needed. So sometimes you will be hollowing it out. Sometimes you will be cutting it, and sometimes you will be using some Boolean operations. And sometimes your sourcing CAD model is not great. Means it might have taken from reverse engineered data or some sort of thing which the surface which it badly needed some smoothing of your models, and then even it will be performed on this sort of tools or the softwares. Or sometimes we need to visualize in a more better way. You have some hinges or wherever you have, then we need to give it in a different colors, or we need to inverse the flip triangles. Means you have a triangle and you have a normal. So normal should be projecting from outside. It should be, but sometimes some triangles may be flipped out, or normal should be flipped out, then which we need to say inverse it back. So we need to flipping it back, either a triangle or a normal for that matter. And you have certain stitching features where you can say automatically stitch if at all some triangle is missing or mismatching or overlapping or intersecting. Something may happen. You may get doubt why it should be happened. You have done your modeling in a very nice way. Yeah, I do agree, but your tessellation algorithm may not be much robust enough to say represent your model in a better way of STL file. So then obviously it may have these sort of errors or the problems which we need to rectify further, maybe by adopting these sort of tools. And some automatic triangulation or some manual repairs can also be done through these tools. And then in addition to that, the support structure generation. So you may get doubt that the supports has been already done in a software which is interfacing with your 3D printer. Yeah, you are correct. But even you may have the other tools which it can even give much options rather than which it may not be available in your software sometimes, or even it may not be customized as for your requirement in many a times. So then you can adopt the support structures. So as for your feature, say I have I have a large surface area which I need to give support. So for that matter, I need to go with a block kind of a support. Simply, I can pick a block kind of a support. So it will fetch me a large surface sort of feature. Or sometimes my feature is somewhat very narrow, which I need to provide the supports. So in this case, it is not advisable to go with the block support. So simply I can go with the line kind of a support. Or even I have a sort of very small feature, but it requires some support. So then I can go with the point kind of a support. Or I have some other occasion where I have much overhang here. So then I need to go with the gusset kind of a support. Or I have a circular cross-sectional feature, I need to give a support. So then I can go with the web kind of a support, something like that, which even it can have many other options to. But if your inbuilt software is having, that's fine, which we can make use of it. But which you are looking more options, but it is also possible to get in done through these tools. And of course, the slicer software, it could be a open source software, or even it could be a proprietary software. So many a times, if it is an SLA or a VAT-based system, or if it is a FDM-based, that is a extrusion-based system, which you can go with free softwares like Cura or Repeater, or you can have Slice 3R, or you have plenty of softwares which it will come as a free of cost to use a slicer module in it to slice your either STL file or a OBJ file or X3D or a 3MF or AMF or any sort of file format which you are trying to say do a slicing it. So basically that is a pre-processing. You have design and pre-processing and generate a G code and send it to the printer. So that is the typical G code which you can come across. So your slicer, which it will create a tool path, it's more or less is more intelligent. So based on your geometry, it's going to design your file that has been designed, and you have say percentage of infill to save your 3D printing time and material, and support structure if necessary, and that all that aspects which your slicer software will be taken care. And even more or less now it is an open source. That depends what sort of printer you're using it. So based on that, you can pick. And to name or to list some of the STL repair, say, softwares or the tools which you have plenty. Some of them may be proprietary softwares like Magix, or some of them may be open source like Mesh Mixer, NetFab, MeshFix, MeshLab, and you have other say STL repairing tools, and of course slicer softwares which we are talking about, Cura, Simplify 3D, and all these are open source softwares, but it may not be work for all 7 3D printing technologies, but it is at least work for 1 or 2 technologies which it will support, which you can use it. Or otherwise, your vendor or a supplier may be giving, along with the machine, these sort of slicer software. And coming to the other aspect is like say topology optimization and the bionic designs. So the topology optimization nowadays is very well-known optimization criteria, design optimization criteria, where you can come across these sort of topology optimized structures. So right from the aerospace industry to um, so automobile or any other industries where they are using this sort of topology optimized structures for, so maybe less material usage, so these designs can be done. Or even you may come across a sort of generative design where you can consolidate the parts. Say you may have say 8 number of components may be consolidated into a single part. So that is the generative design. Or even it may be a sort of bionic design or a lattice structure, um, or more inspired through a biological structures. So even it could be that done that designer's mind, like where so he or she wants to make more lightweighted structures. So then you can have the tools to do this job, maybe right from the Autodesk or parameters or frustum or entopology or altair. So you can find several tools to do this sort of topology or generative or a parametric or a lattice structure or bionic designs. But how do you get fabricated your optimized structures more into these things? But definitely your 3D printing technology is only the one solution to get maximum benefit out of this bionic designs or the nature inspired designs. And coming to the various softwares or the tools available, so you can find several. Just I listed a few here, maybe Altair OptiStruct, or even you may have Abacus Atom or MSC and Nastron, or you can use several say tools. You can find several proprietary softwares or open source softwares, but majority may be proprietary softwares which have listed out here, so which you can make use of these tools to design your things. And further it should be tuned or as for your 3D printing machine or the technology that you're going to use it, right? So as it is, you cannot say send it to 3D printing machine. Why? Because we need to see the constraints of the machine that we'll talk a bit now. So maybe next couple of slides may discuss about that. But like you have the topology optimized structures which you can, and we do simulate say before you send it to the machine. So this is a typical 3D expert software from 3D Systems for metal powder bed based system. Say for that, you can do a multi-physics, multi-scale modeling of 3D printing process. Then why you want to do this simulation? The same logic you can extend, like where you can say find out some sort of errors or some defects, like you may find so model distortions or residual stresses inside your within the layer or with the interstitials of the two adjacent layers. We need to say reduce those sort of errors or the defects maybe in order to compensate your distractions, or in order to compensate your, say, warpage, shrinkage compensations, which you can even simulate them. And even you can do a model of the support structure optimization to have a lattice kind of a structure, or a point kind of a support structure can be adopted here. Or even why you want to do this is then it will have a minimum risk of your printer damage. Say something like your tool collision in case of a CNC. Maybe it may happen here, your recoater or a roller. Say I'm talking about a powder bed system. So where your recoater may hit your part or the layer that you have already sintered or melted. So then which we need to say do a simulation, then you can come to know that there will be a problem at a particular layer, so which we need to say reslice it, or something like that, which we need to do. And even it will also minimize the number of build tryouts if you're doing, and erroneously if you're say sending or you're firing the components. But we don't have a luxury of say buying a material. If it is a titanium, maybe 25,000 rupees per kg of powder. So definitely we don't have a luxury of this, which we need to see the simulation stuff where you can minimize or reduce this sort of wastage or optimum utilization of the resources. And even you can predict sometimes the post-processing requirements, maybe heat treatment or hot isostatic pressing like hipping or support removal, or even any sort of post-processing which you can predict the impact of that even in the simulated environment. So even it can optimize the build orientation as we discussed previously, and you have a support configurations and verify sort of say distortions or the plastic strains or the residual stresses. So it is predominant. Why? Because you have,
Excuse me, sir. So sorry for the disturbance.
yes,
One of the participants is raising her hands for asking something.
yes, please. Yes, please.
Mr. Babu, so tell me, sir. Mr. Babu. So sorry, he's not responding.
Maybe
You may text me, sir.
okay, it's okay.
Chat box, we will answer.
Okay.
Sir. You can continue.
Yeah. Thank you. So then in this way, where you will be simulating these builds before you go actual fabrication of these. When if you see some of the softwares or the tools available to do 3D printing simulations, even nowadays you can find from a conventional CAD CAM, CAE softwares, even from the ANSYS also you can find some. Additive print is one of the simulation kind of a module, and 3D systems, 3D expert is a thing, and Geonex, and you have Verfac, and from ESI you have additive manufacturing, and of course you have a Dizimat from Extremes, and you have other softwares. You have from even Hexagons, Simufact, Additive, and from Autodesk, Netfab, some extent even you do simulate, or from Siemens you have a Sim Center. These are some of the simulation softwares which you can find from the 3D printing area. And the next part of my presentation, then how do you get selected your 3D printing technology? So of course, by material. Why? Because you cannot process all the materials in a single printer. That is another constraint which we need to talk about. So if you see the materials choices, you can go with polymers, that is thermoset, either thermoset or thermoplastic, or metal alloys, ceramics, composites, functional materials, electronic materials, shape memory materials, or bionic materials, or food or constructional materials, or anything like which you can have other than engineering materials. Even it will be supporting other materials also. And coming to the feedstock material form, maybe a powdered form, or maybe a filament form, maybe wire or a rod or a sheet or a laminate or a liquid. So this as for ISO ASTM standard. So seven classes of this 3D printing processes. So, but you can find other. Normally, you can find these FDM, SLA, SLM, SLS. These are the proprietary names, but they have standardized to keeping a generalized name under each category. So these are the 7 categories. And of course, materials as broadly like maybe polymer, thermoplastic, thermoset. You have material jetting or SLA or a DLP is quite convenient with a thermoset kind of a resin, epoxy resins, the photosensitive polymer resins. And you have a thermoplastic like ABS or nylon or those sort of materials which you can process through SLS or FDM technology. Or metals, like you can have a lot of metals, and even sand or ceramics, composites also not included here, but nowadays a lot of developments are happening. So these materials, you have a good number of material choices in the recent times. And the application wise, how do you get selected your technology? So for that matter, first just let me give you an overview of these 7 processes. So with the perspective of a feedstock, either liquid, powder, as solid, as I mentioned, or you may have the 3D printing or additive manufacturing principle. So it may work sometimes like a polymerization process. Sometimes some technology work with a inkjet printing or a binder jetting, simply liquid jetting or atomized, or your powder is atomized or powder is melted and solidified, or simply joining maybe a filament or maybe a sheet, so it can be joined. So you have different principles that you're going to apply, and of course the respective feedstock forms maybe, and you may use an appropriate, of course, the source of energy, maybe laser, maybe electron beam, maybe plasma sometimes, or maybe simply a jetting technology, or you can use some catalyst, or then you have these principles, and of course the 7 processes. I'm not going to talk much on this, but just an idea like how these principle of working and the processes in a nutshell I want to give. That's what this. And then functionality, the functionality wise, the application wise, say if you are looking some sort of form fit applications, then what could be the tolerance range you are looking at, and choose an appropriate say technology as for your required tolerances. Why? Because not all the machines will give the same tolerance values. So then we need to select an appropriate technology for your right application, whether high strength applications, maybe less than 30 MPa or 30 to 85 MPa, or greater than 85 MPa, then you have to select these processes based on your application. Special properties, you're looking at some chemically resist material, or heat resist, or flame resistant, or biocompatible, or flexible material, high elongation, or soft, or rubber or elasto, or kind of a material. Then you can choose an appropriate say technology for your right application. So sometimes your application demands good visual appearance and which your smooth surfaces, then or sometimes it may be more transparent, then you may have an appropriate technology. Or you're looking some textures, so wood fill textures or textures or the metal fill or rubber like, so or full color capability, maybe in polymer, maybe in sand. So then you can use material jetting here and binder jetting here. Then appropriate selection should be done. And last part of my presentation that talks about the design rules for 3D printing. So the design rules, like you can take some features, some standard features. So then how do you say come out with some sort of general design guidelines or the rules? If you are having some supported walls like this, which we need to have this sort of feature, and you have a different values, minimum, that you should not go beyond this value, which you may not be able to get this feature, for example. So if it is an FDM system, you can only go with 0.8 or more than 0.8, but it should not be less than 0.8 of this thickness, or it is 0.5 in case of SLA, or it is 0.7 in case of SLS. So like that, even next slide will talk you about the other processes also. But what I'm trying to say is, like, based on your feature, then we need to check the capability of the machine. Some unsupported wall, which you should not go less than this value, particular machine, then which we need to know this. Otherwise, if your design consists of less than this dimension, definitely you cannot realize that sort of features, and you may be blaming the technology or the machine. So this machine is not giving this feature. So that which we need to understand these constraints rather than each and every process. Like sometimes it may be overhang, and then what could be the overhang, minimum overhang angle, or you have some embossing and engraving combination features, and then accordingly we need to check these things, and horizontal bridges sometimes, or you have a small holes. So anything less than 2 diameter you cannot realize in FDM based system, but it could be realized up to 0.5 in case of SLA, and 1.5 maybe in SLS. And if you're looking these kind of things, so we have some design handbook for 3D printing, so you can refer further. So and other processes, the same features which you can have the other processes versus your features, which we discussed. And similarly, you may have some connecting or moving parts, so then it may go differently, the value, and some escape holes that we need to provide in order to remove your build material. So if it is tedious, if you're working with a powder bed system or a VAT based system, there will be a chance of escaping your material, raw material into your component. So, and some minimum feature, minimum size of the feature, and pin diameter, minimum pin diameter tolerances, and which you can see the subsequent processes and the values for that. So I will be sharing this PPT, you can go through afterwards. So this I picked from a handbook of 3D printing. And which even we can refer some of the labs, the C labs from, say, Purdue University, that is REID, the sort of C lab. They have developed a sort of what do you call the matrices, like where which we can they have divided this the design of any additive manufacturing systems into different categories, like complexity is one of the category, functionality, material removal, say unsupported features, thin features, stress concentration, tolerance, geometric exactness. So just you can run through your design against all these say measurements, then you will get a score once you run through this test. Then you will get your say score. If the score is say 8 to 15, so you may not be much worrying about uh, the manufacturability by using additive manufacturing process. But if your score is between 16 to 23, so we need to strongly consider a sort of different or the design, considering for the redesigning your product. Or if your score is much higher, like 33 to 40, and definitely it needs to redesign, so which we need to have difficulty in manufacturing through your AM or 3D printing technology, so which you can find these sort of avenues. And then why you don't have uh, a set of standardized rules? Why? Because this is all because once you don't have the much standards, once you have the standards, either it has been derived from the ASTM or ISO or any other organization to give these sort of standards. But that is the major challenge or the major issue of 3D printing, to standardize these say products made through 3D printing process. So if you see, as on date, maybe around 35 standards from ISO as well as ASTM, maybe in terms of design aspects or terminology, or fabrication area, or the feedstock related standards. So which you can find very few are available, but still maybe around 70, 75 under development. So why I'm talking all this is, if you have some set of standard rules saying that you follow this, you follow that, so definitely you can further our efforts will be minimized, or we don't know whether we are going in a right path or not, right? Until unless you have some checks and balances comparing with the standards. That is lagging, of course, here in 3D printing. So let me summarize what I have done for the past 1 hour 30 minutes or so. We started. We talked about the importance of 3D printing design, and we talked some of the 3D printing tools and some softwares and process planning of 3D printing, like the part orientation, how it is getting affected your quality, and your supports structure generation and mesh repair, and slicing tools we have discussed, and tool path generation algorithm, and topology optimization and bionic designs, how it can be achieved through 3D printing, and how do you get selected your 3D printing technology, either based on the material or based on the application. Or we have bit talked about the design rules for 3D printing. So this is what we have talked during this session. And these are some of the facilities we have at NIT Warangal. We have a metal 3D printer that is from 3D Systems USA, DMP Flux model. And we have a couple of Stratasys FDM based technology like Dimension series, Mojo series printers. And we have a desktop based printers like Ultimaker 2 Plus, AnyScan, SenseScan for the scanning equipment, and we have a muffle furnace for post processing of this metal 3D printed parts, and short pinning machine to improve the surface finish of metal 3D printed parts. And we have 3D printing softwares dedicated for the 3D printing applications, maybe for medical image processing and design of implants, which we work on this area, like how do you customize your medical devices, patient matched or personalized or customized. Things can be designed through mimics or and 3D 3 Matix software by using these two softwares, and of course Magix maybe for STL modifications, Catalyst to run the Stratasys make machines, and 3D Expert is to simulate the metal 3D printing for powder bed systems. So these are some of the facilities we have at NIT Warangal. Yeah, I think I have done from my side. If you are having any questions, so I am happy to answer those questions.
Participants, if you have any query, kindly unmute your mic and ask to the expert. Okay, sir. It seems that your sessions is very elaborative and detailed. We didn't get any queries from the participants.
Yeah.
Thank you, sir.
No, I can see 58 participants, but no query means maybe fault with me. I don't know.
No, sir. No, sir. We are getting comments in the chat box saying that the information is very useful and nice presentation like that. Yes, sir. Sumar, sir, if you have any query, you can give.
Yes, sir. What Sagar says is correct, sir. So you have very good exposure in the research area. So it's a very good input for us, sir. Thank you.
Okay. Yeah, somebody is asking some question to start with the school level. Yeah. Santa.
Am I audible?
Yes. Yes, madam.
To start at school level, what type of machine or appliances do we buy for children?
Yeah, madam. Nowadays, this technology is even coming with low cost machines also. You can buy from the market. Maybe if you spend around say 30,000, 50,000 rupees also, you will get a FDM based system, the filament based systems. You can get it, or nowadays you can even assemble your own printers also. Yeah, it may be around 30,000 or 50,000. You will get a machine which it can be very man.
Sir, if we buy, will we get everything together as a set? That is the system plus
correct.
the printer plus the machine. Will we get together as one set?
Yes, madam. Yeah, yes, madam. You can. That's what I'm recommending. Only go with the filament based, FDM based system. So, which you will get a filament that is a 1 kg, approximately 1 kg filament. We will get around say 1,200 or 1,400, 1,400 rupees. So the filament of 1 kg as a consumable. And with the machine, say maybe around 40,000, 50,000, you can buy a machine. And each filament, 1 kg filament, say 1,000 rupees, maybe 1,200 rupees, you can get it. Yeah, that may be nice for the school people to start. And more or less these designs, you can download from some of the open libraries like Thingiverse. There is a one, say, a place where you can find, if you are able to model, that's
can you
fine.
spell that, sir? Can you spell that? Thingiverse. What did you mention?
Thin, Thingiverse. I'm putting in chat box.
Yes, I got it, sir. I got
Thingiverse.
So we can get the design from these.
It's you can get legally, means like you can download it. Yeah, and if you are able to model it, that's also fine. So there's simple modeling of your, say, your students can also be done.
Just a small tinkering lab for them to begin with.
That's good. That's good, madam. Actually, yeah. You can do that. Thingiverse, I think GEI typed it.
Okay, sir. Thingiverse.
Thingiverse, VERSE. THINGIVERSE.
Yes.
Just
sir.
you can Google it, you will get it.
Yes, sir. Yes, sir. Yes.
And like that, you have many more websites where you can some hobby designs or also their hobby sake. You can for education purpose and for personal purpose.
A few sample ones will make our students also think and make their own. It's just to ignite their mind and to trigger.
Yes, madam. You are from which college, madam?
I am working in school, sir. TI Matriculation School, Ambattur.
Okay.
We are planning to start a tinkering lab for students.
Yeah, madam. Even the CBSE curriculum, they are incorporating this 3D printing practice in the plus the even with the school children for the CBSE syllabus.
Yes,
that's a good move. Even to they will be excited. The small kids.
Yes.
You can keep this printer in the classroom and then you can get it printed and show them. That will they will be excited.
That's a very catchy brain age, sir. They will nicely catch such things.
Yes, madam. Yes.
Thank you, sir. Thank you.
Okay, madam.
Thank you, sir.
Thank you.
Thank you very much, sir. In spite of your busy schedule.
No, thank you for that. Actually, I troubled you to change.
No, sir.
A couple of times and say.
It's our privilege to have you for the session, sir. Being a postdoctoral fellow in 3D printing and having various patents in 3D printing, you are the exact option for this 3D printing FDP, sir.
Actually, I worked majority on the medical application side, but unfortunately, I'm not presenting here. But anyway, that is the thing. Thank you for the opportunity given.
Thank you, sir. Thank you very much, sir. The session was very informative and very useful to the participants. On behalf of Murugappa Polytechnic and the Department of Mechanical Engineering, our heartiest thanks to you, sir, for sparing your time to deliver the session with us. Thank you very much, sir.
Thank you. Yeah, thank you.
Dear participants,